My name is Erik Koreman, Senior Researcher at the PWNT Technologies R&D Department. In this video presentation, I want to discuss some relevant aspects of NOM removal by ion exchange. The importance of NOM removal in drinking water production is obvious. We see that there is a worldwide need to further reduce NOM and DOC levels in order to improve the efficiency of downstream processes such as coagulation, advanced oxidation and disinfection, and to improve water quality in terms of color, disinfection byproducts and biostability. In principle, there are two technical and economical feasible methods to achieve this goal. First, we have coagulation, a well-known method designed for turbidity removal at lower pH to remove more DOC. A more recent method is anion exchange. Depending on the raw water characteristics, ion exchange can be performed with packed beds, fluidized beds, or suspended ion exchange reactors. Between coagulation and ion exchange, we distinguish some differences with respect to NOM removal. With enhanced coagulation and high coagulant dosages, a part of the humics can be removed as well as the majority of the more hydrophobic and higher molecular weight fraction, the so-called biopolymers. Ion exchange, however, allows us to achieve further removal of humics and organic acids and therefore overall DOC, as the spectrum also shows us. And even further removal can be achieved by increasing the resin volume. Since biopolymers can be substantially removed by subsequent micro or ultrafiltration membranes, these findings explain why there is a worldwide growing interest for ion exchange focused on NOM removal. Ion exchange is a specific chemical process by which dissolved ions are exchanged for other ions with similar charge at the surface of a so-called ion exchange resin. Most anion resins are preloaded with chloride or hydroxyl ions. When we expose the resin to a liquid solute like surface water, these weakly adsorbable anions are at least partially replaced by tri- or bivalent anions like sulfate. The same applies for small monovalent anions like nitrate, as well as bicarbonate. And also for negatively charged NOM or DOC macromolecules. The extent to which dissolved NOM molecules are exchanged depends on their position in the so-called anion selectivity range. While there exists a preference for the resin to adsorb highly charged small anions, the question becomes relevant where we can place the dissolved organic fraction of the NOM in the so-called selectivity range. To figure this out, first a suitable resin for substantial NOM removal must be selected. We can do this, for instance, with a jar tester. From numerous jar tests at the PWNT laboratory, it was concluded that the strongly basic gellular so-called type 1 copolymeric resin was the most suitable for NOM removal from various natural raw waters. The ion exchange process itself can be understood by studying the sorption kinetics. First, because of the intense agitation in the jar caused by the impeller, we have an intense surface renewal frequency and homogeneous conditions all over the reactor. And because of this, for a relatively low resin content, we already observed significant anion and DOC removal. The sorption kinetics can be simplified using a first-order kinetic model that shows us that the non-equilibrium adsorption kinetics are being governed by a rate constant, as well as a residual equilibrium concentration. As earlier mentioned, during adsorption, chloride counter anions adsorbed onto the resin surface are gradually exchanged with dissolved anions in the water to be treated, leaving a loaded resin and a treated liquid with lower anion content but increased chloride levels. Since UVT transmittance at 254 nanometers has proven to be a good surrogate parameter for DOC, we observe a gradual increase of UVT during ion exchange due to DOC sorption, which indicates that the resin is able to remove DOC. Furthermore, we see that UVT and DOC removal increases with both increasing contact time and resin concentration. Depending on the resin concentration, the adsorption time required to reach a near equilibrium state amounts about 25 to 30 minutes, which is a reasonable contact time for pilot or full-scale suspended systems. In this situation, we have about 50% bicarbonate removal, between 60 and 80% DOC removal, and more than 95% sulfate removal, and 50 to 60% nitrate removal. And of course, increased chloride levels due to exchange. This increase depends on the total amount of milliequivalents that are being exchanged. After the liquid phase is separated from the resin is collected, in case of a suspended system, for instance, in a cone-shaped hopper, and periodically transferred into a so-called regeneration column. When the hopper is filled, it is emptied under gravity force to the regeneration column. And after drainage, the resin is ready to be regenerated. The regenerant is a sodium chloride solution. And once in contact with the sodium chloride solution, the loaded resin is exposed to an excess of chloride ions that force the sorption equilibrium back to the left side, leaving a resin in its original state and the so-called spent regenerant or brine containing the desorbed anions that were first removed from the raw water, and some residual chloride that was not used for the desorption. Finally, the regenerant is displaced by an equal amount of rinse water and disposed of as a so-called spent regenerant. The amount of anions adsorbed onto the surface of the resin in the near equilibrium state depends on the total raw water anion content. For some UK waters that were investigated, the anion content is low, and as a consequence, the same applies for the amount of adsorbed anions. Somewhat higher amounts can be found for Lake Mälaren in Sweden, and especially for Lake IJssel water and water from the river IJzer in Belgium, since both raw waters have a high alkalinity and sulfate levels. So finally, we may conclude that ion exchange is a suitable pre-treatment for DOC and color removal, especially for typical PT waters with high DOC and color and TSS. Depending on the raw water DOC and UVT, DOC levels can be reduced with 60 to 90%, And UVT can be improved with 10% to 50%, depending on the DOC-UVT relation. Total anion content has a major impact on the resin exchange capacity, counter anion desorption, and thus total salt demand during regeneration. Thank you for your attention.